Hello everyone, thank you for joining me today as we discuss accumulation and the fundamental theorem of calculus. Our main ideas today are approximate area using our Riemann sums, analyze the behavior of accumulation functions, evaluate some definite integrals using antiderivatives, that's the fundamental theorem of calculus there, and also we'll finish with some U-substitution. So let's start here with what appears to be some sort of free response style problem. This question is going to force us to do some Riemann sum approximation here. You can pause the video and read this paragraph now if you want to. Ultimately here, we are asked to find an approximation for the number of liters of oil that are in this tank at time t equals 15. And we have to recognize that in this table, we are given values of R of t, where R of t is the rate at which oil is pumped into this tank. Okay, so knowing what we know about accumulation, if R is the rate and we want the number of liters, we need to do a definite integral here. We need to find the area under this curve R of t. We need that accumulation of that rate. Okay, so here's the big picture here. To find an approximation for the number of liters of oil in the tank at time t equals 15. We are told that at the beginning of this situation, when t equals 4, there are 50 liters in the tank. So we're starting with that much. And now we're going to add this accumulation from time t equals 4 to t equals 15, the accumulation under this curve R of t. If we had the actual function rule for R of t, we would, find an antiderivative for it perhaps, or if this were a calculator question, use our calculator to do it. We don't know the actual rule for R of t and we don't have its graph. All we have are selected values from the table. So like the problem says, it says using a right Riemann sum with 3 subintervals, we're going to approximate that area. Our 3 subintervals here will span from 4 to 7, from 7 to 12, and from 12 to 15. Okay, so we're going to use 3 rectangles basically, where the heights of those rectangles are dictated by the right endpoint. This is a right Riemann sum. So here's interval 1, interval 2, interval 3. It's the right endpoints of those intervals that will be our heights. And the bases of our rectangles are those distances from 4 to 7, from 7 to 12, and from 12 to 15. So, using our geometry formulas for areas of rectangles now, that first rectangle has a base of 3 and a height of 6.2. Our second rectangle has a base of 5 and a height of 5.9. Our third rectangle has a base of 3 and a height of 5.6. And now it's just a matter of doing some multiplication and addition here to get our answer. And you can pause the video and practice that now if you like. We're looking at 114.9. This was the number of liters at t equals 15. If this had been asked for a left Riemann sum, we would have used the left endpoints. And we would have ignored 5.6, for example. If it had been a trapezoidal approximation, we would have used our trapezoid formula. Areas for trapezoids, you take the height, divide by 2, and add the sum of the bases. Okay, that would be if this had been a trapezoidal approximation. Okay, moving on. This was a huge part of what was chapter 6 for us. Analyzing the behavior of an accumulation function. So here in this situation, we have an accumulation function g of x. It's the accumulation of the area under this curve whose graph we are given, this curve f, starting at -2 and going up to whatever x value we plug in. Okay. The fundamental theorem of calculus comes into play here. I'll talk about it when it comes to that. First, though, part A here asks us to find g of -6 and g of 3. Let's start with g of -6. This is part A. G of -6, we're going to plug -6 in for x in this function g. That's the area under this curve f from -2 to -6. Now the first thing we'll do here is recognize that these bounds are backwards here. We want to start at our left end and end at the right end. And we can flip those around provided we put a negative symbol in front of this definite integral. That's a property of definite integrals. So we have to find the area under this curve f from -6 to -2. Well, let's take a look at this curve f. From -6 to -2, we're looking at a triangle with a base of 4 and a height of 5. Well, 1/2 base times height, 1/2 of 4 times 5, 1/2 of 20 is 10. So the area under this curve is 10 With our negative sign in front, then, our answer here is negative 10. Let's try g of 3. Plug 3 in for x now. So here's the accumulation of the area under this curve f from negative 2 to positive 3. Well, here from negative 2 to 2, we have a semicircle with a radius of 2. So we do 1/2 of pi r squared. In this situation, run that and you'll get 2 pi for this area. From 2 to 3, we've got this little triangle right here. Using our area formulas, 1/2 base times height. The base is 1, the height is 2. That's going to end up being a value of 1. But remember, this area is below the x-axis, so it needs to be considered a negative 1. And so here we have 2 pi, and we add that to our negative 1, and we'll just leave it in terms of pi there. There is g of 3. Moving on to part B, we are asked for g prime of 0. Well, this is where the fundamental theorem of calculus comes into play. If g is this accumulation function of the area under f, I'm not going to go into the specific details here because this video is already going to be probably too long. The idea here is that g prime is this function f. F is the derivative of g. So really, we have a situation where we're looking at the derivative graph in front of us. This is the graph of f, which is the derivative of g. Okay, and I've noted that, and we need to note that when we do free response questions of this style. So I'm going to write it down here. G prime of x is f of x. Fundamental theorem of calculus tells us that. So if we're going to find g prime of 0, really we're looking at the graph for f of 0. So I zoom in here. Here's the graph of f. F of 0 is equal to 2. Not hard in terms of showing work, but hard if you don't know the connection between g and f. F is the derivative of g. Sticking with that now, this is the same problem, so we still have that case where the derivative of g is this function f, whose graph we have. Part C, find all values of x on the open interval from negative 6 to 3, where g has a horizontal tangent. Determine whether these points are local maxes, local mins, or neither on the graph of g, and justify our answers. Okay, so recognizing that this is the graph of g's derivative again, we have to treat this as a problem where we're looking at a derivative graph. So find all the values where g has a horizontal tangent. Well, g of x has a horizontal tangent. Horizontal tangents means the slope is 0. So g of x has horizontal tangents where g prime of x equals 0. Okay, so we need to look at the graph and figure out where this happens, where g prime of x equals 0. So here we go. Here's the graph of g prime. It's the graph of f, which is g prime, the derivative of g. Where would we have horizontal tangents on this graph here? Well, let's take a look. Horizontal tangents where g prime is equal to 0. Well, g prime is equal to 0 here and here. It's also equal to 0 here, but negative 6 is not included on this open interval. Okay, but negative 2 and 2 is where g prime is equal to 0. So let's write that down. This happens at x equals negative 2 and positive 2. Okay, let's consider what happens at x equals negative 2. Well, at x equals negative 2, yes, g prime is equal to 0 at that instant right there, but notice how the graph of g prime, which is the graph of f in front of us, stays positive on either side of that point. Okay, it's above the x-axis. G prime is positive. So in other words, g was increasing, then had a shelf point, and then continued increasing after that. And so at x equals 2, g has neither a min nor a max. At x equals negative 2, g prime of x, which is f of x, does not switch sign. So x equals negative 2 is neither a max nor a min, and I'm going to save a little bit of time by not finishing that sentence. Okay, is neither a max nor a min for that reason. Let's consider x equals positive 2. Okay, g prime is equal to 0 at that instant. There's a horizontal tangent on the graph of g there. To the left of that point, g prime, which is this graph f, is above the x-axis. Then on the other side, it's below the x-axis. So here G prime is positive, which means that G is increasing. Here G prime is negative, which means that G is decreasing. If G switches from increasing to decreasing, picture that in your mind, that's going to be a local max. So here goes at x equals positive 2, G prime, which is F, based on the fundamental theorem of calculus, switches from positive to negative. So G of x has a local max at x equals 2. One more part of this is part D here. Same situation, we still have this accumulation function, so recognizing then its derivative is the graph shown for us here. Find out values x on this open interval where G has a point of inflection. Okay, G has a point of inflection where it switches from being concave up to concave down. Yes, that's true. But how do we tell where it's switching from concave up to concave down if we have G prime in front of us? Well, we're looking for where G prime switches from increasing to decreasing or vice versa. Okay, so before we start writing things down, again, this is the graph of G prime. Where does this graph switch from increasing to decreasing or decreasing to increasing? Well, here it switches from increasing to decreasing. Here it switches from decreasing to increasing. Here it switches from increasing to decreasing. Okay, got to be careful here. It's decreasing and then continues to be decreasing. And so there is not a point of inflection there. Let's take all of this and write it down now. Okay, and there's, of course, different ways that you can organize your work here. I'm going to say it this way. I'm going to say G of x has a, I'm going to abbreviate point of inflection here to save a little bit of time, where G prime of x switches from increasing to decreasing. I'm going to kind of abbreviate here again, or vice versa, or the other way around. Of course. Okay, that's our justification. Now let's write down where this happens. This happens when we found all the spots. It happens at x equals negative 4, x equals negative 2, and x equals 0. That's where the graph of G prime, which is the graph of F here, switches from increasing to decreasing or vice versa. Those are points of inflection on the graph of G. So the key to such a question is recognizing what the fundamental theorem of calculus tells us. It tells us that if G is the accumulation of the area under this curve F is then the derivative. It is the rate of change of G. We need to recognize that and write it down in order to answer these questions correctly. Now, another part of the fundamental theorem of calculus gave us a way to find the area under a curve to evaluate definite integrals, and that is by using antiderivatives. Okay, I'm talking about this part of the fundamental theorem of calculus, which tells us that if we want the area under some function, or we're evaluating a definite integral, we can do so using antiderivatives, then evaluating those at the endpoints of our integration and subtracting those values in that order. So here's such a question where we'll put that into play. We have the graph of f prime. We are told some information about f, and then we need to ultimately figure out the value of f of 1. Notice first that these x values, 0 and 1, are kind of where this area starts and stops. Starts here at x equals 0, stops at x equals 1. So the idea here is that if we have the graph of f prime and we're trying to answer some questions about f, we can set up a definite integral here. Because we have the graph of f prime, and we want some information about its antiderivative, f. The key is using these two values. This is where our region starts and stops. These are the x values used in our question here that I underlined twice. Okay? And so if we use those values as our a and b values, our limits of integration, we can set up this definite integral here, this equation that we can now use to solve for f of 1. We know that f of 0 is 5. We're told that in the problem, so I can plug that in. To the left of our equal sign, this is the area under this f prime graph. Well, what is the area under this f prime graph? This is a triangle with a height of 6 and a base of 1. If we apply our area formula for this triangle, we have an area of 3 right there. So the left-hand side of our equation is equal to 3. Now we can add 5 over in order to solve for f of 1, which is 8. So here's the fundamental theorem of calculus part 2, setting up a definite integral and evaluating it using antiderivatives applied in this context. Of course, there's various other contexts, but here is a nice multiple choice practice question. Finally here, speaking of evaluating integrals, there was a technique that we learned in order to evaluate integrals where we had like a composition of functions in a way, and that technique was U-substitution. The idea is to make a substitution that allows us to find antiderivatives easier. So here's such a problem where U-substitution could be helpful. Of course, if this were a calculator question, we would just run it on our calculator. Okay. The idea with U-substitution is to let U equal the expression that would be the inside part of the composition. We're talking expressions inside of trig functions, inside of grouping symbols, inside of radical functions. Like here, this x squared plus 9, it's a good idea for us to let our U-substitution fill in for x squared plus 9. Okay? Now, since we're working with a definite integral, there's two ways to approach that. I'm just going to teach one way here to keep this short. We got to recalculate what those bounds are in terms of u. In other words, I got to figure out what u of 4 equals and what u of 0 equals, where u is this function of x. So if we plug 4 in for x here, we're going to get 25. If we plug 0 in for x, we're going to get 9. So those are going to be our new limits of integration, upper and lower. We also, though, need to make a substitution for dx here. So the way that I taught it is like this. We're going to come to the side now. We're going to find the derivative of u with respect to x, which would be 2x. But now we can do a little manipulation here. We can multiply the dx over and now divide by 2x. And now we know exactly what dx is equal to in terms of du and x there. We're going to make a substitution in a moment. So here goes. Let's set up our new integral now. Our new bounds of integration are 9 and 25. We've got this x in the numerator. In the denominator, we're subbing in u for x squared plus 9. And for dx, we're going to make the substitution that I circled to the right here, du over 2x. What happens here is that these x's cancel. Now we've got everything in terms of u. Now I'm going to rewrite this a little bit, a couple different ways. First of all, this 2 is in the denominator. It's technically like a 1/2 as a constant, so I'm going to pull it out in front. Then we have 1 over the square root of u, and in terms of finding an antiderivative, it's likely easier to rewrite that using an exponent. Now I can apply my rule for antiderivatives here. I'm going to add 1 to the exponent and divide by the new exponent. Well, if I add 1 to the exponent, I'm going to get 1/2. If I divide by that new exponent, if I divide by 1/2, that's the same thing as multiplying by 2. And we have to evaluate that from 9 to 25. Sorry, my work's all over the place here. Now this 2 will cancel with this 1/2. That's just fine. Now we plug in 25. We've got 25 to the power of 1/2 minus 9 to the power of 1/2. That's our capital F of B minus capital F of A, part of the fundamental theorem of calculus. The square root of 25 is 5. The square root of 9 is 3. We have 5 minus 3 here, which is equal to 2. So there is a U-substitution applied to a definite integral. We can also apply it to indefinite integrals where this step is not necessary because we don't have any bounds to work with. So that was a little bit about accumulation and the fundamental theorem of calculus. Thank you for watching.